working towards the launch of Dragonfly in 2027, 5 years from now, and it should arrive by 2034, which is a particularly useful time on Titan because it's exactly one Titan year after the Huygens probe descended. So it's the same season.
Wow.
So we can exploit the fact that we've measured the winds with the Huygens parachute descent, and we can basically take the seasonal variability out of the equation in terms of what we have to design Dragonfly for.
Episode 105. Return to Titan. Dragonfly. NASA's Cassini-Huygens lander arrived at Titan on the 14th of January 2005. The first instrument to make contact with the surface of Titan was a penetrometer made by Ralph Lorenz. Since then, he's gone on to write many books and work on several other projects. In this episode, he speaks about some of those projects, especially Dragonfly, a return mission to land on Titan. This mission, for which he is the mission architect, is like no other. It's not really a lander or a rover, but a quadcopter that will sample different regions near the landing site during its 3.3-year lifetime. Ralph talks about what we can expect from Dragonfly, which will launch in 2027 and arrive at Titan in 1934. The documentary Destination Titan we refer to in this discussion is available on YouTube. The link is on the web page for this episode.
Lorenz, I and so many other people will know you from that fabulous documentary from 2011, I think, Destination Titan. That was one of the first missions to go to Titan and do some exploration there. Just remind us, what was your contribution to the Cassini-Huygens mission?
Well, I was very lucky. My very first job straight out of university was as a young engineer working for the European Space Agency. This was just when the Huygens project started in 1990. So I got to see and to some extent participate in some of the early design decisions about the probe. And more importantly, it gave me a sort of broad overview of what Huygens was going to do and how it fit in with the broader Cassini mission. But I also saw that in some ways the scientists developing the instruments were going to have more fun in the long term than the engineers who, design the thing, build the thing, it's out the door onto the next thing. But the scientists are thinking ahead. In 1990, they're thinking ahead to 2004 and what they're actually going to find. And I found that very, very compelling. And so I went back to the UK in 91 and did a PhD with John Zarnecki, the principal investigator of one of the instruments on Huygens, the surface science package, and that was great. I mean, doing research, learning all about Titan, and having the opportunity not to be looking at documents and thinking about the big picture, but actually to focus in and to think through what one little piece of Huygens was going to do. What measurement range should this instrument have? What could go wrong with it? And to have the opportunity to literally build it. And that's bragging rights you don't really get very many opportunities for. So I'm sufficiently proud of it to carry something around on my keychain. This is a thing called the penetrometer, and you can learn more about it in the Destination Titan documentary. But it measured basically how hard Titan's surface was at the moment of Huygens impact.
So this was the first bit of the Huygens probe to make contact with the
Yeah,
Titan's surface.
it sort of stuck out of the bottom of the probe about 5 centimeters ahead of the main body, so that it would have a relatively undisturbed penetration of the Titan material. So this is made from the same billet of titanium alloy. It's the same slab of piezoelectric material, and it's a matter of tremendous pride to me that there's this thing sitting 1 billion miles away on the surface of Titan, and there's another one again from the same batch sitting in the Science Museum in London, near the Apollo 10 capsule and James Watt's steam engine. So,
wow.
It's been a privilege.
And penetrometer really does what it says on the tin. It's the first instrument that gave us some indication of the nature of the surface of Titan.
Yeah, it's a very simple instrument. It develops a force history of the resistance of penetration, and from that you can deduce whether the material is granular or whether it's a solid slab, and how hard it is. And what we learned from the specific point on Titan where Huygens landed was that the material was fine-grained but cohesive. Basically wet sand.
Right.
We don't know what the sand was made of, possibly water ice, more likely organic solids, and it seems to have been moist with liquid methane. That had a quite characteristic sort of resistance profile. There was a little anomaly at the start of the profile. There was basically a spike in the force, and we wondered at first if that might be some sort of crust. So you have this sort of softish material with a crust on top, and we did put out the analog of creme brulee, which caught the public's and the media's imagination, which was a lot of fun.
And this is the instrument on the Huygens lander, and it's part of the Cassini-Huygens mission, which launched in 2007 and got there in about 2015.
So Cassini was launched in October 1997, and it took 7 years to get to Saturn. It flew by Venus twice, Earth once, then Jupiter, and then finally at Saturn in 2004. The Cassini spacecraft, all 5 tons of it at launch, carried the Huygens probe. It was attached with a release mechanism, and the Huygens probe was released from Cassini on, I think, Christmas Day 2004. Then it took 3 weeks just flying asleep through space by itself before it entered Titan's atmosphere in mid-January 2005. But then Cassini went on to continue orbiting Saturn and flying by Titan more than 120 times over the next 13 years. So it was a really epic voyage of discovery, and it brought as we slowly mapped out different parts of Titan, it brought the global context to the ground truth that Huygens discovered. So people often ask, well, what's the surface of Titan like? And my usual response is, well, what's the surface of Earth like? I mean, there are deserts that look like this because they've got sand that's been blown by wind, and that selects for particles of a given size, and you get dunes, and that's all very nice. But there are other places where it's liquid that's transported material there, and so you have rounded cobbles that have been, the corners have been broken off as an energetic stream has transported bigger class of material, and that's sort of what we saw at the Huygens landing site. But Titan is a diverse place, just like the Earth is a diverse place.
And there's some remarkable images of those liquids on the surface of Titan. It's liquid, but it's not water.
Right. In many ways, Titan is unique in so many different ways. Not only does it have a very dense atmosphere, which is why Huygens was able to parachute down to the surface, but its surface conditions, the low temperature of 94 Kelvin, and the presence of methane, which is a condensable gas at those temperatures, means there are surface deposits of liquid, and there's actually a hydrological cycle where the liquid evaporates and forms clouds and falls down as rain. And we even saw with Cassini not only places on Titan where there are exposed liquids, some quite large, several hundred kilometers across, so we really call them seas. There's also evidence of river valleys and the stream bed like Huygens landed in. But we actually saw with Cassini methane clouds forming in an area, and then the ground got dark. And then over following weeks, the ground brightened up again. So we know this process is happening today.
Now that process was observed by Cassini from orbit.
Correct, from Saturn orbit. So we'd get kind of views once a month or so of Titan.
And just going back to the science gathered by the Huygens probe, so most of the scientific data it collected was on the way down, whilst it parachuting down to the surface, and then it landed, and then it transmitted for a while. So how long was Huygens operating for during its short lifetime?
Well, that's an interesting story. Of course, when Huygens was designed, we knew next to nothing about Titan's surface. There were ideas that actually the entire body might be covered in liquid methane. And there was actually a requirement that Huygens float. And much of the instrumentation on Huygens was optimized for a possible liquid landing. And that was true of much of the instrumentation on the surface science package. It even had a sonar to measure how deep the sea was. I was a little bit of an outlier in the team in that my instrument, the penetrometer, was optimized for a solid landing, but I did simulation work on splashdown dynamics, for example, which was kind of interesting to do. Because we knew so little about Titan's surface, it was not possible in an engineering sense to be assured of the probe's survival. I mean, you can land on a rock and break up. You could land in some big pile of very fluffy dust and fall to the bottom of it. Nobody knew what was going to happen. So there was no landing gear, there were no shock absorbers or anything like that. There was a requirement that there be enough battery energy and that the probe stay warm enough that it could transmit to Cassini for 3 minutes.
3 minutes?
After the longest possible descent, which was 2.5 hours. What actually happened was that the descent took 2.25 hours, and the probe continued to transmit for actually hours thereafter. But after 72 minutes on the surface, Cassini had flown by far enough that it actually went below the horizon and was no longer in radio contact. We detected the signal from Huygens some hours even after that, but it wasn't possible to recover any data because the link wasn't strong enough to interpret.
That's an incredible story, because you don't, as you say, hardly much detail was available at that time, so you didn't know how long it would take to go through, how thick the atmosphere was, what kind of landing it would have, how long it would last after the landing. And the reason why the time was limited is because, as you said earlier, Cassini was orbiting Saturn, not Titan. So how long would it have taken for Cassini to come back to Titan after the initial orbit?
Yeah, so I talk about the design of the Cassini mission and the Huygens probe in a book, actually, a Haynes Owner's Workshop manual on Cassini-Huygens. To set the stage, Titan's orbit around Saturn is 16 Earth days. Now, some of Cassini's orbits were shorter than that, some were longer. Not all the orbits flew by Titan. Sometimes Titan was at a different point. But typically, over the course of the 13-year Cassini mission, it was kind of a Titan encounter every couple of months. In fact, at the the stage of the mission when the probe was delivered, it was such that the next encounter was a month later, 32 days later. And it's kind of funny, the radar image we took with Cassini's imaging radar instrument, which I did a lot of observation planning for. The image that was taken a month after the Huygens descent was absolutely spectacular. It showed a couple of craters, it showed sand dunes, it showed river channels. They were all instantly recognizable. There had been a radar image taken on Cassini's first flyby of Titan about 6 months before the probe was delivered. And that was very hard to interpret. There were details on the surface, there were things that looked like they might be mountains, there were things that might have been channels, but it was all very weird and exotic. But nobody needed any help interpreting the images from the Huygens probe, because they're not radar, they're in a very familiar geometry, kind of airplane window views. Everyone saw those Huygens pictures and saw, oh, those are river valleys, and the picture from the surface, it's a stream bed with rounded cobbles. And so this radar image that we got a month later, in a way it had some of the thunder stolen from it, but it's all part of building a synthesis, putting the findings from Cassini's different investigations together. Cassini was very formidably instrumented. It had optical cameras, it had infrared instruments, it had a radar, it had radio science to probe the gravity field of Titan, instruments to sniff the upper atmosphere, and it was a big fight in a way to during the development of the Cassini science plan to work out which of these things we do on which flyby, because you want to do everything, but you can't point a radar that faces this direction and a camera that faces this direction at Titan simultaneously. You kind of have to put everything in line and then work out how quickly you can turn the spacecraft, and that science operations plan development was a big activity during the long cruise we had to Titan.
In addition to the technical side, you refer to the Haynes manual that you cover all the technical details. One of the things that I found, and it leaves a very special memory for me, is that documentary by Steve Slater, Destination Titan. I know how I responded. What was it like for you from your end in making that documentary? What influence did that have, do you think, on your career?
I don't think that particular documentary had any specific career influence. Cassini and Huygens were, of great public and media interest, from the get-go. So over the years, I've probably done a dozen, maybe more than that, documentaries. My first flight in a hot air balloon was on a TV shoot. My first flight in a helicopter was on a TV shoot, gesticulating out of the open door to Lake Mead, actually near Las Vegas, and explaining how there were features that you could see there that look like what we see on Titan. So at the time it was just another interview, sit and get mic'd up and answer some questions. So it was what was interesting, of course, was the human story in Steve Slater's Destination Titan. Steve Slater, the producer, was himself only a teen, I think, when the Huygens encounter happened, and it's a great story that he was so inspired by the event to feel the motivation to put together a documentary on how John Zarnecki, the PI of the surface science package and my PhD advisor, how he himself had got into building an experiment for this epic space mission and seeing it through, and all the challenges that you have to overcome. What I didn't appreciate, for example, when I started as a PhD student, is that the principal investigator on a space mission or an instrument, it's not their job to be like the world expert on Titan necessarily. The job is to assemble a team and to make things happen and to figure out that you need to find an international partner to provide part of the hardware because your own funding agency isn't able to give you the support you need, and to find the right people to do the very different jobs that putting together this kind of enterprise requires. So it took me actually a few years to realize the challenges that John had to address.
And I think that's quite interesting. My perception of that film and what it meant to me was different because of my age, and because you were quite young when that happened. It's sort of automatic, natural way of developing a career, I guess. But yeah, it was really terrific.
Well, in fact, one of the earliest, maybe the earliest TV appearance I had was John Zarnecki was getting involved in the Open University, and they decided to put together a program, a course on design for an alien world, I think it was called. And one of the things they did was they did a couple of TV shoots at the University of Kent, where we were based, and building the hardware. And you can see, me with less belly and more hair, with an early development unit of the penetrometer. But they also set up a video diary, basically a vlog, I suppose you'd call it now. This was long before blogging was a thing. But there was this sort of little booth with a camera set up, and we could sit in front of it and, just say what was on our mind, what the achievement of the day had been, and it was fun to do a couple of those. And so that Open University program, I think, was maybe my first TV appearance, and maybe that had a bigger impact career-wise. I don't know.
It's a lovely phrase you used. I remember reading a letter from Arthur C. Clarke's archives back in 1939. On his first attempt, he couldn't join the RAF. He said it's because of the presence of spectacles and the absence of teeth. That's the reason why he couldn't. So the team that built Huygens and the team you worked with, as with most missions and most projects, once they come to end, those teams disperse. Do you still keep in touch with some of them? Are they still working in this field?
Absolutely. I mean, it's now 30 years on.
Wow.
Careers move on. People go on to do other things in completely different domains. One of the things I noted, I did an article for Aerospace America a few years ago called "Engineers Are Dogs, Scientists Are Cats." We're both doing technical things, but the mindset, and in particular the organizations that we're in, are quite different. Engineers, as you say, are very project oriented. They're responsible for delivering something. Right. Then once it's delivered, that's it, you're done. You check the box, you move on to the next thing. And in fact, engineers work in groups. It's kind of like a pack, right? They move on to the next thing. Scientists are more like cats, more territorial. They're trying to kind of take possession of a problem, and that they'll work on it even if they're not being paid to work on it, right? Because they want to solve it. And so in a way, the scientists are easier to keep track of over the years because they hang on to that problem and maybe work on other projects that are related to that problem, whereas engineers, just go on to whatever they're assigned to. So I certainly stay in touch with many scientific colleagues, including John Zarnecki. In fact, as it turns out, one of the key players in the surface science package development, the project manager, in fact, Mark Lees, who's in the Destination Titan documentary, he's still around in the space instrumentation business. And in fact, I am now sort of in the position John Zarnecki was. I lead an instrument development for Titan, an instrument called DragMet, the Dragonfly meteorology and geophysics package. And it has many of the same sorts of sensors advances that the Surface Science Package has. And in fact, we are coming up in just 2 weeks on our preliminary design review, basically where we rack up the plans for how we're going to build this instrument and how we're going to test it. I mean, launch is still 5 years away, but you need a very consolidated design, very secure plans to be given the authority to move ahead. And part of that review process seeks external experienced subject matter experts, and actually we've been able to pull in Mark Lees as a reviewer. So since he's been through all this stuff and knows what's involved in setting up a test facility and the customs paperwork and just all the extra complications you don't think about. So definitely stay in touch with a few people.
That's a brilliant bit. That's really, really interesting. I forgot to ask you. You mentioned in your early career you worked with ESA and then you did your PhD with John Zarnecki. But before that, maybe when you were doing your GCSEs, was space something that you saw as a future career at that point?
So I was always interested in space. I mean, I think I remember getting a book on rockets and stuff when I was 4 or 5. The early 80s, when I was a teen, I did entertain, fantasies of flying in space. I mean, the space shuttle was going every few months then. There were even expected to be some British astronauts. And so I sort of had vague ideas about going into aerospace, but 3 things happened in very quick succession in early 1986. First, Challenger blew up, and that kind of derailed a lot of thoughts of human exploration. At the time, I think I started having to wear glasses, and so I, no longer the perfect human specimen. But there was also the Voyager encounter at Uranus, which had been sort of expected to be a bit of a dud. I mean, Uranus was just this sort of, fuzzy blue planet. But it turned out to have a ring system, and it turned out to have a very diverse set of satellites, and that was really interesting, and that kind of underscored the planetary exploration thing. And then there was the Giotto encounter with Comet Halley, and that was Europe's first planetary mission, even though Comet's not a planet. And there were Europeans with whom I could identify. Leading the discussion of the new images coming down from the camera, and John Zarnecki had participated in the development of the dust impact detection system on Giotto, which recorded this sort of machine gun rattling on the bumper shield, and so that was very, very dramatic. And I guess that's probably where I first came across John Zarnecki. So those 3 things together really kind of set me on thinking about unmanned robotic space exploration, planetary exploration, as what I wanted to do. And talking with the school career counselor, they're not used to people having such a well-defined goal. So it was sort of, well, I suppose you should do maths and physics. And in fact, I was then soon after confronted with this sort of engineering science dichotomy. You don't, as a teen, have a good appreciation of the difference between those disciplines. And I think I ended up making the right choice. I ended up doing aerospace systems engineering at Southampton, and that was great. I mean, I had to sit through all these classes in structures and fluid mechanics and stuff that I wasn't that interested in because I wanted to work on, astronautics. But there's all the stuff about guidance and radars and so on that was very applicable. And of course, the great irony is that, I was very fortunate to get my first job in ESA working on Huygens, and of course there's lots of experienced spacecraft engineers there, but Huygens had a heat shield and a parachute, and they'd have to do wind tunnel tests, and so the aerospace engineering training was useful. And I even had a class in helicopters, which was kind of exotic and interesting enough at the time. And 20-30 years later, I'm getting to apply that background to the development of Dragonfly, a rotorcraft lander at Titan, which of course has caught a lot of people's imagination.
Before we move on to Dragonfly, Huygens was a European Space Agency contribution to the Cassini-NASA. That's a joint mission. But you worked with NASA, ESA, and also JAXA. What's the work that you've been working on? What's the mission you've been working on with JAXA?
Well, of course, one of the great things about planetary exploration is it's an international endeavor. It's what I think Carl Sagan called the modern pyramids or modern cathedrals. It's an enterprise that harnesses the talents of thousands of people, and it's an opportunity to work together instead of being at war with each other or whatever. Cassini was US led, but actually had instruments from Europe on board, and vice versa was true of the Huygens probe. Since the early 90s and Cassini-Huygens, and even a little before, there are other players in the planetary exploration domain, and among them is Japan. Japan actually launched a couple of distant flyby spacecraft to Comet Halley. In around about 2010, they launched a mission called Planet C, or the Venus Climate Orbiter, which was renamed Akatsuki after launch. And there are often arrangements in international missions where the partnerships. So, for example, NASA has supported Akatsuki with providing support from the Deep Space Network to get more data back from Akatsuki. And as part of all that, there are several scientists based in the US who participate in Akatsuki, myself included. And I work on an instrument called the Lightning and Airglow camera. Basically, it's a very high-speed photometer to detect flashes, possibly from lightning. And indeed, we seem to have detected an event. What was really kind of interesting about Akatsuki was that it was launched in 2010, and in the summer sometime, I think June or thereabouts. And I got the call from NASA in November saying, "Congratulations, you've been selected to be part of the participating scientist team, and there'll probably be a meeting in Japan in the next month or something like that, or 2 months." Anyway, not many weeks later, the orbit insertion of Akatsuki was due to occur, and it fired its engine, and then the engine cut out. In fact, the nozzle fell off. I mean, there was a remarkable chain of events, which was very well documented. The engineering telemetry really shows what went wrong, and it's a fascinating story I wrote about in an article online. But the mission wasn't lost altogether. It failed to go into orbit around Venus, and it just kind of sailed past and went into heliocentric orbit. But the mission designers at JAXA were able to figure out a tentative recovery plan. They put it on an orbit that would go around the sun, I think 10 times, for Venus is 9 times or something like that. But basically it was going to be 5 years in space, closer to the sun than they had designed the mission to be, but it would come back to Venus. And they had just enough propellant left to use the little attitude control thrusters to limp into a very elliptical, non-ideal orbit around Venus. But 2015, I got the call from NASA again saying, "Well, I guess you were back on." And so actually for the last 6 years or so, I've been closely involved with that mission, and that's been a lot of fun. There are different aspects of culture and the way teams work together. You have to exercise a certain amount of diplomacy. Talking to brash Americans is very different from reserved Japanese colleagues, and so you need to think about communication is a big part of science, and communication is a big part of the engineering of large projects, and there's good lessons there.
And it's a fascinating story when things go wrong on a mission, and particularly the Japanese. I think they had a similar problem with their first mission to Mars, and how they recover from that is perhaps even more interesting. So
Yeah, I did a book some years ago with Dave Harlan called Space Systems Failures, where we sort of try to rack up a lot of the anomalies that have occurred on space missions, and it's remarkable. There are a lot of lessons that don't get learned. You know, the same things go wrong time after time.
you're now based mostly in the US, is that right?
Yeah, I'm at the Johns Hopkins Applied Physics Lab, which is just outside Washington, D.C. APL is one of the, let's say, three big mission developing centers for planetary exploration in the US, the others being JPL and the Goddard Space Flight Center, which is actually quite nearby. So, APL did New Horizons and Messenger at Mercury and the Parker Solar Probe. So it's done quite a few really quite challenging and interesting missions.
And they are interesting, but one of the most interesting that's in the pipeline, and I think everybody's interest has been piqued by what Ingenuity has been doing on the surface of Mars. The mission one of the many things you're working on is Dragonfly. So tell us about Dragonfly. Where's it going? When is it going? And what's it going to do when it gets there?
Yeah, so Dragonfly is what we call a relocatable lander. It's basically an octocopter that is the size of the Perseverance rover. I mean, it's huge. Now, in fact, it in many ways, its origin traces back to some work I did around about 2000. I was working with JPL on studies of balloons and airships on Titan, and as I looked into how much power do you need to drive an airship, and thinking about how does an airship access surface material, analyze the sand in the sand dunes, for example, you realize that maybe a lighter than air platform, aesthetically appealing as it is, isn't actually the right choice. I mean, hot air balloons are great for champagne breakfasts on your wedding anniversary when you know the weather's going to be good. But if you want to go any place, any time of your choosing, search and rescue or inserting special forces into hostile terrain, use a helicopter. And then when you sit down and work out, how much power a helicopter would need to fly on Titan, it's actually 38 times less than the same size, same mass vehicle and same rotor diameter on Earth. And so, I had a paper out in 2000 saying, here's a helicopter idea, and it was before its time, right? Everyone's thinking, well, how do you make a vehicle fly itself? There's lots of challenges, and of course we hadn't been to Titan with Huygens yet. It was still very much an unknown environment. But fast forward 20 years, and we've had the drone revolution, right? You can go to an airport gadget store and get a little thing this big that just flies happily around. And so the technology is there to actually execute this vision, except it turns out it's an octocopter, not a helicopter, and there's packaging considerations for that. Helicopters have very mechanically complicated gearboxes and swash plates to control the orientation of the rotor blades, whereas it's actually quite simple to control the speed of a directly driven rotor with an electric motor. So that's why we've gone with that architecture. It actually turns out that the programmatic origins of Dragonfly are completely independent from the Ingenuity helicopter. And Ingenuity is a true helicopter with the swash plate and the changing blade incidences. And in fact, this question comes up so often that I actually put together the sort of parallel developments and the different challenges these vehicles have in a book called Planetary Exploration with Ingenuity and Dragonfly that the AIAA has just published. Mars is a really, really hard place to fly. The air is so thin that the rotor blades have to claw really hard at the air to develop enough lift. And so aerodynamically, it's hugely challenging. There are other aspects of the Martian environment and the infrastructure we have at Mars that make things a lot easier, right? Ingenuity is a small vehicle, a couple of kilograms, and it uses the rover to relay its data via orbiting satellites to the Earth. And so it only needs a small battery, a small radio. It has a little solar panel. whereas we are, a billion miles away from Earth, and we had to send the data directly to Earth. It's a very cold environment, so we need to use the waste heat from a radioisotope generator, like the one the Perseverance rover has. In fact, we use its waste heat as well as the electricity from it. So there's a lot of big differences between the environments and the purposes of the vehicles and their design, and those are laid out. But we are working towards the launch of Dragonfly in 2027, 5 years from now, and it should arrive by 2034, which is a particularly useful time on Titan because it's exactly one Titan year after the Huygens probe descended. So it's the same season.
Wow.
So we can exploit the fact that we've measured the winds with the Huygens parachute descent, and we can basically take the seasonal variability out of the equation in terms of what we have to design Dragonfly for.
So I'm not aware how big Dragonfly is going to be. So it's going to be easier to fly in Titan because it's a thicker atmosphere, but of course no sunlight, so no solar radiation. So you're going to use RTGs, as you were saying, for the power source. Will it be accompanied by an orbiter?
No, Dragonfly is a standalone vehicle. It has we intend a radioisotope power supply. It has the instruments on board to do the scientific investigations, and it has a high gain antenna, basically a 1 meter dish that flips up and beams the data direct to Earth. Dragonfly was selected in a competitive mission program called New Frontiers, which New Horizons, OSIRIS-REx, and Juno were all flown under. And that mission series has a well-defined cost cap, and there's just no way to put an orbiting relay inside the cost cap as well as the vehicle, so we had to make the vehicle self-contained. That will mean we can't send as much data back to Earth as we could if there had been an orbiting relay, but we've designed the instruments and the science plan to maximize the science content out of every bit. We use a lot of data selection and data compression techniques, and we have the luxury of employing those that Huygens didn't, in part because of the computing technology, but also Huygens was a one-shot deal. It had to operate in real time and hose the data out because it didn't know it was going to survive the landing. On Dragonfly, we switch on, we take data during the Titan day, which is 8 Earth days long, and then there's an 8-day Titan night when we're out of view of the Earth and the Sun. It's dark, and basically we just recharge a big battery from the 100 watts or so trickling out of the RTG. And during that time, we can be on the ground looking at little thumbnail images sent down, or overview data products, and then zero in on events of particular interest, or a picture of a particularly interesting rock or whatever, and then tell the lander to beam that down. So we have the opportunity to really enhance the efficiency, if you like, of the operation. Dragonfly, though everyone's excited about the fact that it can fly, it will only fly a fraction of a % of the time, basically half an hour for once every couple of Titan days, so once a month or so. And it can fly several kilometers in a hop.
Several kilometers?
Yeah.
Wow. And just one question about the entry, descent, landing. I presume because of the, again, thick atmosphere, will it just be a parachute?
So we enter inside a heat shield, much like the Huygens heat shield, or that on Perseverance. We deploy a drogue parachute, which stabilizes that body through the transonic region. And then it takes about nearly 2 hours to descend to the lower atmosphere. We'll throw out a bigger parachute at that point to let the heat shield fall away cleanly, and then the vehicle will lower and drop out from the back shell about 1 kilometer above the ground, and then it flies under its own rotor power down to make its first landing.
So it's going to activate its flying mode
during descent.
That's even more interesting than Sky Crane. That's it's going to be an exciting EDL.
There will be a few tense scientists and engineers during that last part of the descent. Yeah.
And then, as you say, it's what sort of lifetime do you envisage at this point?
So the nominal mission on the surface is planned for 3.3 years. That's in a way a budgeting thing. You have to have something to design for. Radioisotope generator will decline slowly, and all that means is it just takes longer to recharge the battery between flights. So one can hope for possibly a mission extension beyond that, but you have to design the mission to accomplish specific goals. In particular, we want to look at the surface composition in some diverse geological settings, and specifically areas where we think there has been transient exposure of liquid water. We land in an area where we think there will be plenty of safe landing sites, basically in the flat plains between some of Titan's big sand dunes. And then we'll fly from there in progressive hops towards an impact crater called Selk. And there's evidence that this impact event melted part of the crust, melted the ice, made water. That water probably has interacted with the organics that make up the sand dunes, for example. And that interaction yields some very interesting prebiotic compounds, at least as far as we know from laboratory experiments. So seeing how complicated that stuff has got is a goal. So we'll land where it's safe and then progressively march to where it's probably rougher, but more interesting. But we can do aerial reconnaissance, check out sites before we commit to land on them. And in fact, we're working with the Ingenuity team on some of these sort of operational aspects. How do you coordinate flight on another world?
And so from what you're saying, the landing site has been finalized already.
Yeah, that was part of the original mission proposal. You have to build the scientific case. What happened was there are some fundamentals of the astrodynamics of arrival. Basically, we come in from interplanetary orbit straight into Titan's atmosphere, because that way we don't need to carry the propulsion for any braking burns. We can just use Titan's atmosphere to slow us down. That and the tolerance of heat shield materials basically says you want to aim at the side of Titan that is receding from you, basically the backside as Titan goes around its orbit, because it's tidally locked. So that kind of set a hemisphere, and there's some entry angle considerations that kind of put you on a ring of locations, and then you want to land so that the sun is still up and you still have good Earth view for 72 hours after entry, and that kind of narrows that to a sector, which is still quite a big sector. And we just looked at the map of Titan, and this crater just kind of leaps out at you, saying, this could be interesting. A lot of people ask, and it would technically be possible, but it's not the right thing to do scientifically. Actually, the Huygens landing site happens to be like 1,000 kilometers due south of there. I mean, it's not that far on the map of Titan, but it's longer than we can fly, and so we're not expecting to go and visit the heroic corpse of Huygens.
And scientifically, that would be interesting. I see what you mean. So when we're expecting it to arrive at the Titan?
So arrival is just before 2034, one Titan year after Huygens' descent.
Right. And then finally, I've been impressed with how many books you've already written. What are you working on now, and what are you working on maybe in the next round?
So just before Dragonfly came up, I was working on a book on Titan seas with a colleague, and the notion of exploring them with boats and submarines, and what we learned from Cassini about their composition and the waves, and it's a really fascinating environment. So I'm trying to get back to that. Looking beyond that, one of the things I've been most involved with Dragonfly and other missions is understanding how spacecraft and their instruments work in planetary environments. How do you figure out what risks are acceptable? how big the waves are going to be on Titan seas, for bobbing around on them, how hard are the rocks you're going to have to drill, how much dust is going to fall on the solar panels, and working on these environment specification kind of aspects and risk management has been really interesting. So I think I might do something along those lines.
Well, until later this decade and perhaps the next one, I'll catch up with how all this is progressing. For now,
Look forward to it.
Dr. Ralph Lorenz, thank you very much indeed.
Thank you, Gurbir.